Hello! What I'm drawing here is two syringes connected by a rubber tube here, where you can squish down on here and it will lift up on there, or squish down on here and it will lift up on there. It's a imitation of a hydraulic system, which I'm sure you all have at least heard of. Hydraulic fluids, what they do is they transfer pressure equally throughout the system, and so that's actually the basis of our happy time today is that's a big word, Al's principle. I forget who it's named after, but what it says is it's Mr. Principal, yeah. What it says is the pressure applied anywhere inside a confined fluid is equally distributed everywhere in that confined fluid. So the pressure, just pick a spot, I don't know, right there, spot 1. The pressure at location 1 is equal to the pressure anywhere. It doesn't matter, I don't know, there, that's spot 2. And so P1 is equal to P2, which means the force divided by area is equal to the
force divided by area.
Force divided by area. Oh. Which means if you have a very small area, you can have a very small force. And then if that area increases, like I tried to draw this as a little fatter than that one, but if that area increases, then the force will also
increase.
Very good, increase, which means you can exert a very large force by simply having a larger area connected to an item that has a lower or a smaller area. You can exert a smaller force, which is how hydraulic systems work. All right, so anyway, it's based on Pascal's principle. The force at location 1 divided by area at location 1 is equal to the force at location 2 divided by the area at location 2. All right? All right, so then what you can do is you can say, all right, what's the area of this syringe? What's the area of that syringe? And I can say, all right, if I'm applying however many pounds of force here per that area, that ratio of areas will tell you the extent to which the force is then multiplied. Cool? All right, now, the barometers here, you guys hopefully all know how those were invented. They took just a big old barrel of, in that case back in the day, was high quality mercury. And they really took, just think of a giant test tube, a really big old test tube, and filled it with more high quality mercury. Oh. Huh?
We're trying to refocus it.
Oh, there. It'll get there.
It's good.
Then, say it's full way up to there. Stick your thumb over top of that sucker, or flip it over, stick it underneath the surface of the mercury. And then let go. Just let it go. Someone should write a song.
Let it go.
I know. So it would look, I don't know, something about yay sticking out of the mercury, right? Atmosphere, the bank machine pushes down. And that then takes pressure going up, right? Huh? Huh? The height from there to wherever it goes above it is a whole lot of
vacuum.
Very good, nothing. There's a whole lot of a vacuum up there. So the height from here to here is, you guys all know what the atmosphere can push up, right? In millimeters mercury is
76.
Ooh, that's close. 760 mm Hg.
Digit-wise, it's close.
I know. Not bad, not bad. Okay, now, what we can do then is say, well, gosh, if that's how high it is, what is the pressure of the mercury there? Or what's the density of mercury? I could ask you that. What's the density of mercury? If you know that is the height of this column, which again, I wouldn't use millimeters, use very good meters, 0.760 meters. Mercury, right? The pressure is equal to,
Force over area.
ooh, that's cool. Okay, yeah, I'm with you. And again, remember, what is it that's supplying that force?
Weight.
The mg over a, and this is what we did the other day, right? Another way to spell mass is density times
Area. Volume.
volume. Yeah, if you remember, this mass is the same thing as the density times volume times gravity, which if I divide that by an area, again, the area kills 2 dimensions of the 3 dimensions of the volume, right? So if this is a length times a width, this is a length times a width times a height, rho GH is pressure. Okay? So rho GH. So that pressure is equal to rho GH. You know the H. You know what planet you're on. You know the amount of pressure in pascals is atmosphere. You remember what that is?
1.
It's 1 atmosphere, and then in pascals, it's
101.25.
something like that, 1.013 e to the 5th. That's one bank machine. So this pressure is that, the density is what we're looking for, pressure divided by GH is the density of mercury, or the density of anything. So the pressure is going to be 1.013 E5 pascals divided by 9.8 meters per second squared times 0.76 meters. All right? So, all right, let's just do ish math here. This is 10 to the 5th divided by 10.
10 to the 4th.
10 to the 4th. 3/4 of 10 to the 4th.
0.75 times 10 to the 4th.
Yeah, 0.75. Well, we're divided. Actually, it's not 3/4. Sorry, it's that divided by 3/4, which is clearly 4/3. Sorry,
times 10
ooh,
to the
geez,
4th.
inverses fractions. They're so divisive. So 4/3 of 10 to the 4th. 1e4 times 4/3. That's 4e4 divided by 3. It's what, a little less than 4, right? 4e4 times 10 to the 3rd, which, I don't know, magic box. Darn it, if I only had a magic box. Perhaps I could do this equation all at once. All right, so let's do this. We'll talk 1.013 E5 divided by 9.8 times 0.76, and that is clearly 13,600, which is ish 10 to the 4th, 4/3. Wow, gosh. And that's kilograms per
Meter. Seconds.
cubic meter.
Cubic
Yeah.
meters.
Kilograms per cubic meter. And that is ish the density of mercury. That's an accurate thing when we start looking up densities. Whoa, look at that. Density of mercury, 13.6 times 10 to the 3rd.
Wow.
Physics. Even under that kind of pressure. Let's pretend in our headsies we do the exact same thing, but we don't use mercury. How about some high quality H2?
0.
Oh. Okay. But what I could ask you then, instead of asking you the density of high quality H2O, because that's something you already know, then I could ask you how tall or how high would that column of H2O be? And then we would use the exact same formula. I'll just rearrange it. Instead of pressure being rho GH, well, I mean, it'll be H equals pressure divided by rho G. Which means the pressure stays the same. 1.013 E5 PAs. I'm going to divide it by the density of H2O, which again you know is 1,000 kilograms per cubic meter, and we are still hanging out tragically on planet Earth. So, this is 10 to the 5th divided by 1,000. That makes it 10 to the 2nd, right?
Yes.
3, we'll take 3 away, that's
Yeah,
100,
10.
and divide that by 10, that's
it's
going to
just
be 10-ish. That height is going to be ish 10 meters is how tall it would be, 30 some odd feet, and 10.3-ish meters. Okay, cool, huh? Simple. So we could make a barometer out of any liquid if you wanted to, as long as you know its density, or you could calculate its density and figure out based on its height, or you know, whatever, right? You might even be able to figure out what planet we're on. All right, next thing I'm going to do is change this up. Let's pretend this is a rubber tube or a piece of plastic tubing. So it's a tube
That was beautiful.
in the shape of a U. I wonder what they'd call that.
Unicorn.
A U-shaped tube.
A bowl.
Hmm.
No, not a bowl. It's not a bowl.
Are you being
I'm
serious?
just kidding.
I don't know, maybe we'll watch a video on it or
It's
something.
like that.
But
Those
anyway,
tubes that they use in the plumbing.
you guys don't know.
I'm just making it more entertaining to watch.
Oh, well, clearly I need some assistance with that. If you pour some high quality H2O on one side of that U tube, it'll trickle down and it will find itself to a happy equilibrium point, same height on both sides, right? Simple?
C, senor.
That's easy. HL, the height on the left, will be equal to the height on the right. Eh?
Yeah.
Eh?
Yeah.
If you were standing right there, how much pressure would you feel above you, or based on the fluid that you're at the bottom of? You would feel the pressure of the
Air.
air, the atmosphere, the bank machine. And the same thing right there, the pressure due to the bank machine. Atmospheric pressure. What if you go a little below the surface? Let's say you're right there and there, again, equal heights below the surface. The pressure you feel to the water on the left is the rho of the H2O times the gravity of the planet times the height of the water on the left. Rho GH. That's going to be the exact same as the rho GH R, because it's the same fluid, it's the same liquid, it's the same density, it's the same planet, and you're the same depth below it, right? Simple? So this sounds awfully similar to what we started the day with. The pressure at any one location is equal to the pressure at any two location. And in the case of a U-tube, what we're referencing is equal heights. Okay? But now we're going to change it. What if I pour water on this side, let it come to equilibrium, but then pour some other liquid, like mercury, 13,600. That's a tad more denser, isn't it? What if I pour some high quality mercury in there and the two liquids don't mix? So if they don't mix, can you see that all that mercury that's much more denser is going to push that water up? Right? So if I were to redraw this, then I would have to say the surface of the water might be up there, and the surface of the mercury might be, I don't know, maybe to there-ish. So all of that is mercury, and all of that, all the way up to there, is water. Does that make sense? Because mercury is a lot more dense, it pushes the water up higher. So now we have a difference in height, don't we? A delta H. So this is the height of the HG, or HHG, I should say, HHG. This is, that is the height H2O. Cool? And what I can say is, well, gosh, the sum of the pressures at any one location is equal to the sum of the pressures at any two location. If you happen to be right there and right there, then the amount of the pressure above you is the same. Okay? So, let's say the height of the water. Actually, we can even move it up here, even it doesn't matter if you want to do it right there. That would be easier. Let's do it right there. At the interface of the two liquids, right there at the edge. Huh? Let's pretend this height is, I don't know how tall you want it to be.
20 meters.
20. Yikes. It's
YouTube's
pretty
a big
ambitious.
place.
YouTube has
Two
a lot of
centimeters.
a lot going on. Why don't we call it just 2.0 meters? Huh? That's a tad more realistic. If that's the case, then can we figure out the density of mercury, even though we already know it? But we could calculate it, couldn't we? Because I got pressure, atmosphere, the sum of the pressures at one location equals the sum of the pressures at two location. What's the sum of the pressures at one location? Right there.
H times G times P. Or rho. Rho.
Times G times rho H2O. It's going to be the same thing as the pressure right there at the second location, which is the ATM plus the rho GH HG, right? Hmm? Okay? Alright, so what do we got? The ATMs die because it's the same thing on both sides. The rho GH of the H2O equaling the rho GH of the HG. Which means I do have to do it lower than the surface, don't I? It does need to be below the surface, because if that's a 0, guess what this whole side is? Very good, more nothing. So, if I know this, then what I could do is calculate how much higher this column of HG is. So the height of the H2O could be 2. G is 9 point. Ooh, right after that, it doesn't even matter what planet we're on, does it? Alright? So, this divided by the density of the mercury will give you the height of the mercury. So the height of the water is, what do we say, 2 meters times 1,000. And that's kilograms per cubic meter. And I'm going to divide that by the density of mercury, which we figured out over there is 13,600. So this will be 13,600 kilograms per cubic meter. And that will tell me the height of the mercury above me. So I would have to, again, be below the surface in order to make that math work, because if that height is 0, that whole term becomes what war is good for. Absolutely nothing. All right, so what is this? 2,000 divided by 13,000? 2,000 divided by
20 over 13.
13,600, which I'm dancing around. 0.147, and that's meters, which is 14, 15-ish centimeters. So 15-ish centimeters will get you the same amount of pressure as 2 meters of water, 15 centimeters-ish of mercury. Cool? Huh? Gosh, Pascal, he had principles. All right, and one other thing. What if we then swapify one side of this, it doesn't matter, for something that is connected to a chamber that has gas. Oof. Bad night at White Castle. So, if this has some gas in it, and there is liquid in this pipe, then what we can say is, gosh, let's pretend in our headsies that that gas has a certain amount of pressure that pushes the liquid up to, I don't know, there-ish. And the other edge of this liquid is, I don't know, there-ish. Okay? So this whole region there is full of water or mercury, whatever you want to call it. Okay? Then, if I were to say, well, gosh, what if we are hanging out right at that boundary, right there? The pressure that you are feeling is the pressure of the gas, right? And if you are at an equal height over here, then the pressure that you are feeling is the pressure that is the rho GH of whatever fluid you're hanging out in, plus the bank machine, right? Kids, focus. Clearly. So, we can figure out whatever fluid this density is. I don't care if we tell us the height. How much height would you like to say is between there and there?
5.
5 meters. Which is why we're all now focusing, aren't we? So that's 5 meters. What I'm going to ask you is what's the pressure in the gas? And what you'll do is say the sum of the pressures at one location is exactly the same as the sum of the pressures at any two location. The only difference here is pressure at location 1 is due to the pressure that the gas itself is exerting. And the pressure at location 2 is bank machine plus rho GH. So I got to keep the bank machine there and the rho GH. Okay? Huh? So, all right, I either tell you the pressure of the gas and you tell me the density of that fluid because you know the height, or I tell you the density and you tell me the pressure of the gas. I don't know, it'll have to be bigger than atmosphere. If atmosphere is 10 to the 5th, then let's say the pressure of the gas is, I don't know, 3.7 E5. I just made that up. So, 3.7 E5, pressure atmosphere plus rho GH. All I will do is push the minus button. Pressure of the gas minus atmosphere, which is 10 to the 5th. So 3.7 E5 minus 1.013 E5 divided by GH is the rho. So let's go up here, the pressure of the gas, 3.7 E5. From that I will subtract the bank machine, which is 1.013 E5, get a number, and then divide that by GH, and that would tell me the density of whatever this fluid is. So then divide by G, 9.8, times the height, which is, we just made it up earlier, 5 meters. Okay? So, this one we can do all at once too. What it doesn't matter. 3.7 minus 1.013, and that's 2.687 E5. And then I will divide that by
50.
50. And I'm getting 0.05. This is not a very dense liquid, is it? Oh no, it's E5. 0.0, okay, I didn't do the E5 thing. So this is 5.4, and that's 1, 2, E3. So 5,400 kilograms per cubic meter. Which again That's a lot more denser than water. The gravity of this would be 5.4. It's 5.4 times the density of H2O if you want to do the gravity thing. But anywho, there's that. It's a lot less dense than mercury, remember, which is 13,600. So this is somewhere between water and mercury, which, you know, hey. Yay, physics.